All right, now that we have learned how to compute or calculate the estimator B using the square method, it is also worth looking at the sampling properties of B. So what is sampling properties? Again, that those are the properties that you could conclude by looking at the whole distribution of B over many random samples drawn from the same population. Now, so the first property is the unbiasedness. So the list where estimator B is unbiased. And what does that mean exactly? Meaning, when you repeat estimating procedure on many different random samples, like I just said, now, then you can expect that the average estimate you get from this sample equal or very close to the true parameter beta. Now, for example, graphical illustration is like this. Now there's a whole range of value where B could take. Now, and this is the mean. So I call it B bar, for example. Meaning, for some sample, you can get a value somewhere here, and then here, a bit closer, maybe in a farther away. But when you take the average of all these values, you will get a B bar equal or very close to the true parameter beta. No? And how do we know this true parameter beta? We'll talk about it a bit later. But for now, let's take care of the analytic part first. No? So we can see that by taking the expectation of the solution from our minimization problem before, for B, right? And then replacing Y here with X beta plus epsilon, because that's the specified linear model that we've been working on, right? Here I could even distribute this bracket out. So would mean I have X prime X to the power minus 1 times X prime X beta. Now that is for the first thing. I could draw it like this. Now plus again X prime X to the power of minus 1 means inverse times X prime epsilon, right? So this is the one inside that expectation operator. In the next line, we could see that because this one is a linear operator, the expectation, we could split them into two parts over here, like that. Why it's written that way? I talk about it in a second, but let's look at this for now. So X prime X inverse is the inverse of X prime X itself. And when you multiply the two together, you will get an identity matrix. An identity matrix that is IK. You can check it out yourself using the Excel file or the Excel operation that I show you today now, and then times beta. All right. And then when you take the expectation of this product, you get the beta, because beta is a true single parameter vector, right? So it's a constant, so to say, and the expectation of it is itself. You take it out of the bracket. How about the second one? Why is it like this? No. Because remember from the Gauss Markov assumption A2, we assume that the error and x are independent. So any function of x will not tell you anything about epsilon. And by definition, that means that the expected value of this product equal to the product of the expectation themselves. No? So you could split them into two different expectation operator because they independent. We learned that last week. Okay. Then the next Gauss marker assumption needed here is this one is 0. Now, the A1 assumption on average, the expected value of epsilon is 0. Therefore, the whole term is 0. Now, so at the end, the expected value of B equal beta itself. And therefore, the estimator B is unbiased. Next, we look at the variance covariance, or shortly variance matrix of B. Now, because B is a vector of coefficients or parameters inside. So just like the case of the vector epsilon, it has a variance covariance matrix also. However, let me remind you first one thing, that like in previous slide, we have shown analytically, just analytically, we didn't plug in any numbers, didn't use any samples to arrive in the unbiasedness of the estimator. So here, similarly, we could show that the variance covariance matrix of B equal to the sigma square times x prime x inverse. So here also we could show that analytically using some of the results that we have derived in the previous slide, but we're not going to do it here to save us some time. Then you may have an impression already what the variance covariance matrix looks like, right? It has the variance of each coefficient, each B1, B2, until Bk on the main diagonal. And of the diagonals are those covariance between different B's, and they are symmetric around the main diagonal. Now that we have learned already. Let's go back here. What's the sigma square? The sigma square so far we denoted is the variance of the error terms, right? So the variance of epsilon, constant for all epsilon, right? And times the whole matrix x prime x inverse. Now, so if we know the data, we have the data, and if we know the variance of the residual or the errors, then we could derive already the covariance matrix of B. Nevertheless, in reality, it might be hard to know this sigma square because we don't know the true residual, right? And we come to that later, how to deal with that. Okay, then how good is B actually? It can be shown again analytically, just like before, mathematically or theoretically, that B has the smallest variance of all linear estimators. Variance here means the variance of the sampling distribution that I draw on the slide before. And it is the best linear unbiased estimator. Usually we put the abbreviation of it, blue, easier to remember. No? Best linear. Unbiased we showed before already, linear, because our model is linear. And it's actually a function of x and epsilon, right? So it's linear. Estimator, of course, we're talking about estimator, so it's blue. And this is even with non-normal distribution of the error, Why? Because remember when we talk about a Gauss Markov assumption A1 to A4, we didn't mention anything about the distribution of the error. What is that distribution? Nothing about normality. So this holds even for non-normal distribution of error. I couldn't get rid of it, sorry. Okay, the next point. Then if, in addition to the Gauss Markov, we assume normally distributed errors. But stop here a bit. The properties that we have shown on the slide before, and this blue property could only be achieved when we have the Gauss Markov assumptions hold. Now, let's stress on that a bit. Now, in addition to the Gauss Markov assumptions, if we also assume that the errors are normally distributed, so we have normal distribution, then B is normally distributed as well. Why? Because B is just a linear function of the error term, right? And a linear function or linear combination of the normal distributed random variables also are normally distributed random variables itself, in this case, the whole vector of B. Okay, what does that mean? Meaning we could put it in the notation of the normal distribution like this, would mean expected value beta we have seen, and the variance covariance matrix sigma square times x prime x inverse, right? And in this case, with this normality assumed, we could even say that B has the minimum variance of all unbiased estimators, MVUE. And what is the difference from the one above, from the blue? Because here we also take into account all the non-linear estimator. So they also beat all either linear or nonlinear unbiased estimator to become the most efficient one with the smallest variance. Okay, like I said before, we could prove these properties analytically. However, maybe more intuitive or convincing if we could show it with real numbers, right? And the nice thing with simulation is you actually can control or know the true parameter, or we call this the data generating process. So we know what the beta actually is. So the principle, the idea is the following. First of all, you draw some random residuals first. So it's kind of going reversely from the estimating procedures we usually do, right? First, we estimated the B, and then we calculate the residual. In this case, we draw randomly the residuals first. And from normally distributed distributions, right? And then we calculate the dependent variables using this kind of functions. Okay, so you have different dependent variables value depends on which residuals it takes from the sample. Then we could regress these dependent variables on the x. So x are given beforehand. So it's deterministic in a way. No, nothing random with x over there. And then we could do the regression of this created y on x once using OLS, and the other use list absolute deviation estimator. So it's another linear estimator, but instead of using the square distance from the observation to the line, it's using the absolute distance. So take the absolute of that distance instead to estimate beta 1, beta 2. Usually you don't see that often, but in some cases it's proven to be appropriate to use this method. Then we collect the beta 1 and beta 2 for each of this regression, and we repeat this 2,000 times. Meaning we draw 2,000 samples, regress its samples using this equation, and collect the beta 1 and beta 2. And then we can compare between the OLS and the LAD. What we can compare? The sampling statistic, the mean, the average beta 1 from OLS and the average beta 1 from LAD, for example, over 2,000 samples. And then see also the variance. So this I will show you on R. Okay, so this R script is called OLS Monte Carlo. I put it on eCampus, so you can check it on yourself. So, like I said, the first thing I always do, remove all the object. And I set the sample size 100, so 100 observation for each sample. And we need some certain package for plots and drawing sample also. We have two random variables, and like I said, we draw 2,000 samples. And then there's also the whole setup below to prepare like the place where you put the result, the estimated parameter in, and so define the variance covariance, the sigma, and then have a loop to regress the equation and collect the parameter. I will not run everything I will not show everything, but for now we just need to run the loop, the simulation. And what we're interested in is to see the mean of the OLS. This is for beta 2, because we have 2 beta, right? 2 parameter, so this is beta 2. From OLS, the average over 2,000 times now. And what was the average of the LED? So both are very, very close to the true parameter that we set before, which is 10 over here. So you see 10, and this is 9.999 something, and then 10.000 something, right? However, so that, first of all, that means that both are unbiased, right? To be sure. However, let's compare also the variance of these sampling distributions now to see how the variance are. So here the variance of the OLS is pretty small, 0.0003 something. And then, well, it's a bit larger, you see, for the less absolute deviation. Maybe it's hard to say. Let's look at the histogram of it. There we go. So the green bluish one is for OLS, and the pinkish orangish plot is for the LAD. And you can see that the tail here for the pink part is fatter, meaning the probability or the likelihood that you end up a specific sample end up here to the edge, far away from the true parameter, is larger for the LAD. Now, so that is one way you could check it on your own, the sampling properties of the OS, even though usually we only have one sample to work with, right? So by now, I hope you have realized that the uncertainty that we're concerned with about the estimator B is from the fact that we're working with only one sample of the data, not the whole population. Most of the cases, because in reality, this is not possible. For example, if you want to measure the height and weight of the whole human population on Earth, imagine how long that would take, possible at all. In other cases, may be possible, but not recommendable. One example is your blood test. You don't want them to take all your blood out for that, do you? Right? So working with sample is unavoidable and even necessary. And we just have to deal with it. Unfortunately, the nice properties of the OS that we have seen previously, the unbiasedness and efficiency, they're called the small sample properties. And not always the case that they hold in reality. But first of all, what is small sample properties? That means the properties that hold even for small sample, not only for small sample, but even for small sample now, when certain assumptions about the errors met. And here we're talking again about the Gauss markup and the normality assumptions like we have seen. Under many circumstances, if not the majority of circumstances, only the large sample properties can be shown for the estimators. So the large sample properties means the properties that can only be shown for large sample when the sample grows bigger and bigger. And the idea for this comes from the asymptotic theories, which ask the question, what happens if hypothetically I could increase the number of observations until infinity? So for OLS, using some inequality and probability theories, we could show that the estimator B is consistent under the classical assumptions. What is consistent? First, let's look at this probability and what is inside. The one inside says the distance of your estimator B from the true parameter beta. Then this distance is smaller than any small arbitrary number residual. So the probability for this as n grows to infinity will converge to 1. Put it differently, I could say that the probability that our estimator converge to the true parameter when n grows to infinity is 1. And this is thanks to this matrix x prime x inverse when n grows to infinity, very, very large number, that will converge to 0. Why? Because you remember x prime x, this matrix x ultimately has n involved in there because it's the number of observation, right? You have x as n times k elements, right? So the more observations you have, the larger n you have, the bigger these elements inside this matrix. And then at one point it will grow very, very large. And then when you inverse it, ultimately you will get very, very small elements inside, and it will converge to 0 when n grows to infinity. Then your estimator B will converge to the true parameter beta. So sort of a comforting thing to know that, okay, if I have more observation, my estimator gets better in terms of approaching the true parameter. And this is called the probability limit of B equal to the true value beta. Estimating sigma square. So I mentioned that sigma square is a theoretical parameter now. So it's a true parameter of the underlying distribution, just like beta, but we don't know what it is. So we need an estimate for it, just like B is an estimate for beta, right? So we can denote it as E and define it as the difference between the true value of the dependent variables. This we have, right? This is what you have the moment you open your data set. Minus the estimated Y. Usually the estimated value is denoted with this hat, right? Yeah. And then equals Y subtracting X times B. Pretty trivial. Then we could, from this E, calculate the unbiased estimate of the error variance sigma square. And we denote it again as sigma square hat. Now, this sigma square hat could be calculated as E prime E. So the inner product of the vector E divided by n minus k. So in other words, sum of square estimated error divided by n minus k. And what is this called? You must know it already. The decrease of freedom. Right? There. Note, however, you may realize the difference here. Why n minus k? Because didn't we say that the variance defined just by the average of the distance from the mean, right? So in that case, you better divide by n. Nevertheless, that will give you a biased estimate of the variance. Again, because the sample is typically small now. Therefore, we correct for the degree of freedom and divide by n minus k. Once we have this estimate of the error variance, we could also replace it in the calculation for the covariance of B that we have seen some slide previously. So we replace sigma square by sigma square hat over here, and we arrive to the cov hat of B. That will be necessary for your hypothesis testing later, as you will see, especially with the simple famous t-test. We need that covariance, the estimated variance matrix of B.